This is 6.2.3.2. We're now going to relate DTFT to DTFS for a single period of a periodic sequence. So this xn is this periodic sequence here, and of course we can extract a single period out of it and then put zeros to make it aperiodic. And at the bottom, this is the aperiodic sequence, or I should say a single period of the periodic sequence. And because now these have finite support, finite meaning that only a certain set of values are non-zero and the rest are zero, then we can use the DTFT directly, because now this computation is feasible. We are not computing for all xn samples, we are only taking one period to compute x of omega, the DTFT of a single period. We will show you that the results that we find is related to the DTFS of the periodic sequence through this equation. Let's see why. We'll go to the next page to see the equation, to recap the equation for the DTFS. We take a single period of xn and we evaluate ck's at these frequencies. We'll start with 2 pi over n for different k equals to 0 to n minus 1. So these are the frequencies we are evaluating to get the ck's. What about the DTFT of a single period? Now the DTFT of a single period is for n equals to minus infinity to infinity of that single period. Since the single period has finite support only from n equals to 0 to n minus 1, we reduce from this equation to this equation, taking that single period. The difference is that we are examining this single period with all omega, very different from the DTFS, where we are only examining at discrete omega, discrete frequencies at 2 pi over n for different k's. But once we have reached this equation, they are almost very similar. Look, x of n for one single period is exactly x of n here. What about this e minus j 2 pi over n kn? It is e minus j omega n. The difference is that omega is real and here is a discrete frequency. And the other difference is that 1 over n here. So we're going to move this 1 over n to the left hand side such that we now have nck. And this equation, equation 13, is even closer to equation 12, because on the right hand side, it is both are the same. Both are examining xn, a single period, and in the DTFS, we are examining at this particular frequency, 2 pi over nk. But in the DTFT, we are examining the real omega. So what we can conclude is that x of omega at omega equals to 2 pi over nk is the same as nck. That is the conclusion. And what it means is that if we want to express x of omega, the values of x of omega at this particular frequency is exactly nck, and then again we use the deltas to say that in the continuous function it only exists at this particular frequency, 2 pi over nk. So this is the conclusion. Now I will sketch for you the interpretation. I have a single period of this sequence. So the single period is basically some values and then all zeros after it. And if I can plot for you x of omega, so all I need to do is that I take this finite support and then I use the equation over here, which is exactly this equation, and I work it out only for the finite support for all omega. And omega here I'm plotting from 0 to 2 pi. So here is 0 pi, here's 1 pi, and over here is 2 pi. And it is a smooth plot because I basically examine it for very fine values of omega, and you can see a smooth plot. Now, of course, this is then I take this and make it in periodic, and there are different periods here it repeats after every 10 samples. Here it repeats after every here repeats after every 8 samples. Here repeats after every 16 samples, and the last one repeats after every 32 samples. And because this is periodic, then n is different. So n here is 8, n here is 16, and n here is 32. What we actually do is that you then now be able to compute the DTFS coefficient of this, and this. What is the difference? You realize that only n is changing, and of course k is changing. Here is from 0 to 7, and here ck is from 0 to 15, and here ck equals to 0 to 31. But what is actually being changed is that it is these guys. The lines that we are evaluating at different frequencies are now 2 pi. In this case is over n is 8 here. This is 2 pi over 16 here, and here's 2 pi over 32 here. So the spacing between the lines here is resolution 2 pi over 8 times different k. K is 0 to 7. Here k is 0 to 15, and here is k equals to 0 to 31. So basically, by having more and more samples, we are actually dividing 0 to 2 pi more and more finely, and we are finding the ck's lines. And as number of samples goes to infinity, you realize that the lines will merge into this smooth function over here. So this is a relationship between DTFT and DTFS of a single period. So DTFT reveals a smooth spectrum of NCKs. That's it all. Thank you.